All right. Last time we talked about Turing machine enhancements. We said that lots of enhancements don't increase the power. We said that even if you could combine them, non-determinism, multi-tapes, multi-heads, lots of large alphabets, it doesn't do you any good. You can simulate all of that with a single head, single tape. Yeah. Is the mic working? Is this better? All right. All right, so we said that you can combine all these enhancements, or so-called enhancements, and you can simulate with a regular machine, no non-determinism, single head, single tape, single two-letter alphabet, and so on. Now, how many have used JFlap so far? Good, that's a lot more than the last time. Please, the rest of you use it. It's like, if you don't use it, I'm not sure what you're thinking. It's like programming on paper and never using a compiler or never running a piece of code and thinking you can program. So create these machines, make them do things, debug them, enhance them, make sure they work, and then you'll have a better understanding about why this simple model computation can do anything, right? So then we started talking about context, about recognizable versus decidable languages. So we said that a language is decidable if there's a machine that always halts, never runs forever, always gives you the right answer, always in finite time. We're not saying it's going to be efficient. It can take a long time, but finite time. It's not going to run forever. So every regular language, for example, is decidable because there's a finite automaton that accepts it, and the finite automaton never runs forever. It always stops. In fact, in linear time, it stops linear in the size of the input string. It changes one state per character, and at the end of the string, it tells you yes or no. So all the regular languages, for example, are decidable. Then we relax that definition a little bit and say, if you're allowed to run forever, and equate that with a no, with a reject, because it's certainly not a yes, so it's the other one, law of the excluded middle. If we relax that definition like that, then you can recognize more languages than before. Some languages are not decidable, but they are recognizable, like the halting problem. If you're given a machine that halts, you know that it will halt. How? By running it, by simulating it. If it doesn't halt, you'll never know. You'll run with it forever. But that's OK, because now you're allowed to run forever. And that's a reject implicitly. Right? So you're not being wrong by running forever. So we started proving some theorems, and today we'll prove some more. So we already said the halting problem is recognizable, not decidable. And you know, decidability is a special case of recognizability. Because decidability, you must always halt, and recognizability, you may run forever. You don't have to, but you may. So that's more general. And in fact, it allows you to do more things if you take that definition of recognizability instead of decidability as the class of languages that you're looking at. So it's easier to recognize than decide. You may have seen that in real life lots of places. So for example, if you work on a problem, you're not sure what the answer is, it takes you a long time, finally you have some insight, you get the solution. But if somebody shows you the answer and explains to you why it's true, that's a lot easier to believe and understand than coming up with it yourself. Right? So that's kind of an intuitive example from real life. All right, so we talked about enumerators and deciders. So an enumerator is something that just prints out members of the language, strings, one after the other, with some separators so you know where one begins and one ends. So for example, instead of prime numbers, there's an enumerator for prime numbers. 10 lines of code, go through all the integers, one up. For each one that's prime, print it out, separated by dollar signs. This printout will go on forever, but eventually every prime number will be printed by your 10-line piece of code. And importantly, every non-prime number will never be printed. People forget that. So a language is not just what the thing accepts. A language is also not what that thing does not accept. That's just as important. Right? That's why in court they say you got to tell the truth, the whole truth, and nothing but the truth. These are three separate things. Right? They just say you got to tell the truth. Well, tell the truth, but also lie a little bit, but you told the truth, so you satisfied that condition. No, it's not enough. So keep that in mind. Some people made that mistake on the midterm quite a bit. So here's a machine that accepts all those strings. But it accepted all these other strings too, so it doesn't count. Right? Otherwise, a machine with one state, a finite automata, accepts all of sigma star, will accept any other language under this definition, right? Because everything is a subset of sigma star, and that machine with one state accepts every string it's given. But that's no big trick to do that, right? Just like it's no big trick for a clock that's broken to be right twice a day. Think about that. It's not always wrong. In fact, it's right an infinite number of times, twice every day. But it's not very useful as a clock, because it's got to be right not just twice a day. It's got to be right every second of every day and never be wrong. That's when a clock is really good. Same for these machines. Keep your mind straight about that. Okay, so you have an enumerator that prints things out one at a time. It prints all of them out. All of them, all the strings are in the language. It doesn't print anything other than strings in the language. Then that language is printed out by its enumerator, and this enumerator is an enumerator for that language that it prints out the strings for. And the format could be arbitrary. It could be some encoded version, or it could be other symbols besides $signs. So it's not strictly about $signs, but basically it prints out the strings one at a time. And we don't care which order. So we're not saying print the shortest ones first and then the longer ones. We're not saying that. We're not saying print them in lexicographic dictionary order. We're not saying that. We're just saying eventually every string will be printed, and no string that's not in the language will ever be printed. Okay, it'll print exactly the strings in the language and nothing else. No strings not in the language. All right, so first theorem. If a language is decidable, there's an enumerator that prints it in lexicographic order, by dictionary order. By size first, and within size by dictionary order. That's what we mean by lexicographic order, and dovetailing through all the strings. Why is that true? If you have a decider as a subroutine, how can you build an enumerator from it by calling that subroutine? Perhaps repeatedly. So if you have a subroutine that can decide yes or no on every string, whether it's in or out of the language, how can you, from it, build one of those enumerators? It's not hard. We mentioned that in the last few minutes of the last lecture. See if you remember that. Either, how can you construct an enumerator? Somebody be brave, take a chance, feel the rush of speaking up. It's healthy, it's good. Yeah. I have a little tight loop that prints or generates all the strings in sigma star, A and then B and then AA and AB and BA and BB and then AAB and so on. It's very easy to do, right? Generate all possible strings in lexicographic order by size. How many see how to do that with a little 3 or 4 lines of code? All right, that's all. Let me state it again then, because this is very important. We can't proceed unless you get that part. So I want to print out sigma star. 5 lines of code, maybe 10 lines of code. C, Java, C++. Loop. Construct all possible strings. You have 2 characters, A and B. So the A prints out first. That's the first string. Then you print out the B. Then you print out AA. Then AB. Then BA. Then BB. Then AAB. And this loop will eventually do it. How many see how that 5 to 10 lines of code will work? Okay. I wish it was more than just a third of the class. Should we try again? Yeah, question. It doesn't have to be, but we don't need to pull in non-determinism, so let's not do that. And if it was non-deterministic, we already know that you can take this non-deterministic one and convert it to a deterministic one, right? And how do you do that? Well, you basically use a construction from a few slides ago, this one here. So if you have a non-deterministic machine that bifurcates 2 ways, you can take those 2 things, put them on a single tape, every time it bifurcates again, make copies, blah, blah, blah. So you're simulating non-determinism with determinism. So once you understand that, from this point forward, there's no need to talk about non-deterministic Turing machines if you don't want to. Unless there's something very specific you want to say about them, specifically about the non-determinism of them, then be my guest. But from this technique, it's clear that we never have to worry about non-deterministic machines as far as constructing them or playing with them or programming them or whatever, because whenever you have a non-deterministic machine, you can also have a deterministic machine that will do the exact same thing. Now, sometimes it behooves us to talk about non-determinism anyway for lots of other reasons, but not because we have to, but because we choose to make some point. Okay, how many get that? Okay, it's like in finite automata. Does a finite automata have to be non-deterministic? No, because there's a power set construction that allows us to take any non-deterministic finite automata, convert to a deterministic one. So without loss of generality, all we have to worry about is deterministic ones from that point forward. Of course, there could be other reasons why we'd want to talk about non-deterministic finite automata, but not because we have to. Not because they buy us anything extra in terms of the languages they recognize. They may be a little more efficient, or they may have some properties that we want to discuss and split hairs about, but not because they're any more special. So basically, if a language is decidable, it could also be enumerated in lexicographic order. How? What you said a minute ago. Basically, enumerate all strings in sigma star. For each one of those strings, run the decider on. The decider that you have because it's decidable. So you have a subroutine that says yes, no, yes, no, yes, yes. So run every string to the decider, come back with the answer. If the decider says yes, print it out. If the decider says no, don't print it out. For every string coming out of that loop that generates sigma star, all of the strings in lexicographic by size order, the decider will tell you which ones are in, which ones are out, so just print the ones that are in, and now you're an enumerator by exploiting the decider as a subroutine. How many get that? You're called a decider repeatedly, and that makes you an enumerator. Any questions about that? This will only get deeper and more convoluted. We're still in very shallow waters here, so if you don't get this, ask questions now, you'd be better off. Questions. From a decider, we built an enumerator, and we can always do this. This is a general theorem. It's not just about a specific language, it's about any language. Any language that has a decider, therefore, by this construction, has an enumerator by lexicographic order. We'll see why lexicographic order matters a whole lot in these discussions in a minute. All right, so far so good? This is an algorithm of how to convert a decider into a enumerator. Enumerate everything, run them all to the decider. The decider is your filter. Together, that whole construction is an enumerator. Enumerator in lexicographic order. Okay, second theorem. If a language could be enumerated in lexicographic order, then there is a decider for it. That's a little bit less obvious than the first, but together, look, they go in both directions. This says if it's the decider, there's a lexicographic enumerator. This one says the opposite, the contrapositive. This is there's a lexicographic enumerator, there must also be a decider. And together these theorems tell you that deciders and enumerators are equivalent in terms of the set of languages that they encompass each. It's the exact same set of languages. For every language that has an enumerator, there's also a lexicographic. For every language that has a lexicographic enumerator, there's also a decider for it, and vice versa. So decidability and lexicographic enumerability are the exact same coinciding concept. Just like finite automata and regular languages, just like Pushman automata and context-free languages. This is the characterization for decidable languages. There exists enumerators in lexicographic order for all of them. Okay, but we haven't still proved the second part. So prove to me that the language can be enumerated in lexicographic order. You can build a decider from that enumerator by calling that enumerator now as a subroutine. How many understand the goal or the task here that we need to do? Okay, how many understand the statement of this second theorem? Okay, all right. Half of you, fine, I'll take it. Maybe some people don't like to raise their hand, so it worries me sometimes, but that's okay. Anybody want to comment on that? How do you do that? How do you build a decider from an enumerator? I give you a black box subroutine that enumerates stuff in lexicographic order from small to large. The language could be infinite. This list will run forever, but that's what an enumerator does. From that subroutine, an enumerator, build me a decider. How do you do it in general? Maybe somebody who hasn't spoken yet. rather than the usual 5 or 6 or 8 people. All right, go for it. But this is not about finite state machines, right? So you have a piece of code that if you ran it, we're not running it, but if you ran it, it'll spit out the language in lexicographic order, one string at a time, just like that. Right? And from it, we want to build a decider, something that tells you if a string is in the language or not. Okay, so let's just talk about codes. It's easier than talking about Turing machines or automata or states. String comes in the door, and you're the decider. You need to say yes or no. The string is in or out of language. So you're not sure how to do that, but you do have an enumerator. So you fire up the enumerator, and it starts to spit out strings, just like up here. And if any one of those strings is equal to the one that you were given, then what? What do you say? You say, yeah, I accept, and you're done. And you decided yes, and you reported that answer, and you're correct because the enumerator spat out that string for you just then. But let's say it doesn't. After a while, it still doesn't come up, and the language might be infinite. The enumerator will keep spitting out more and more strings. So when will you know that the string at hand is not one of those strings that the enumerator is going to eventually spit out? When can you be sure of that? After an hour, after a year, after a century, after a Google millennia? When? Yes, that's exactly what it means. Exactly. So once you have a string that comes out of the enumerator that's longer than the one you have in your hand, you'll know that the one you have in your hand will never show up again because a longer one just showed up and they ain't getting any shorter, they're just getting longer and longer. So then you can stop and decisively say, no, that string is not in the language, and you'll know that for sure. How many get that? Okay, so it's based on the length. And it's all tied to the lexicographic business. If it was just spinning out strings not in order, you couldn't do this. You couldn't pull this trick of being sure that it will never come out because something longer just came out of the enumerator. This is a general technique. This works for anything that has an enumerator. So whenever you have an enumerator in lexicographic order, you can build a decider from it just like that. So now we have closure here. The circle is now complete. Decidable lexicographic order are the same thing. Okay, we just proved both directions. How many get all this? Okay, that was only a third of you, so ask me questions then. What part didn't you get? And also the part after, get a load of this. Ask me something specific. Yeah. Or I'll repeat the whole thing if you want. Lexicographic order means dictionary order. It means by size first, and then within size by dictionary order. But the important part is what? Size or the dictionary order within the size? Which part is more significant in this whole discussion? Take a wild guess, it's only two choices. What about the lexicographic order? Size is the issue here. It's not within size, what order, because for every size, there's only a finite number of strings for that size. Right? There's only 2 strings of size 1, A and B. There's only 4 strings of size 2, AA, AB, BA, and BB. Right? And for every finite size, there's a finite number of strings of that size. It's exponential, but it's a finite number, and eventually you'll exhaust them all, and you'll know whatever it is you're trying to find out. But So it's not about how you sort within size. It's about the size. Well, you might as well say, okay, sort by dictionary order. And now the order is unique. There's no more ambiguity within order. Okay, so ask me more questions about this. So what have we done? We've characterized the decidable languages two different ways. We said decidable languages by definition is what we said a couple slides ago. It's a language is decidable if and only if there's a Turing machine that says yes or no for every instance. It's always right, always stops, always halts, always gives you the right answer. End of story. That language is therefore decidable because there's a decider for it. Something that always says yes or no, and always is correct, and is always doing this in finite time, never running forever. That's the definition of decidable. It's a characterization, but it's also a definition. So we just came up with another characterization altogether. We said a language is decidable if and only if it has an enumerator in lexicographic order, which is a different characterization than the first characterization, and apparently doesn't even sound like the first characterization when you first hear of it. How can something that's decidable be also something that's lexicographically enumerable? What does one have to do with the other? This is what. Because you can prove it in both directions, and so these two characterizations are equivalent. Just like if I said the set of languages that are regular are the set of languages that are acceptable by finite automata. Okay, that's one definition of regularity. But later we said, okay, a set of languages is regular if and only if they can be represented by a regular expression. That's another characterization different than the first. That doesn't sound like it's the same, but we proved an equivalence. We showed for every one there's one of the other. And that's what we're doing here for decidable languages. We're giving two different characterizations showing that they're equivalent, that whenever a language satisfies one characterization of decidable, being decidable, it must satisfy this other characterization of being lexicographic and enumeratable. I hope I can just make up a word, enumeratable. I verbed that adjective. Anyway, more questions? Yeah. Okay, so the question is a string of infinite length undecidable? Let's just say in this course, there are no strings of infinite length. You could define one and you can reason about them, but that takes us so far afield from what we're trying to do here that even mentioning that, I think, will confuse some people. But let's just say there are no strings of infinite length in this entire course. Sigma star has no strings of infinite length. It has an infinite number of strings, but none of them are of infinite length. The strings of size 1 and 10 and a Googleplex and much larger than that even, but none of them are infinite length. The string has a last character. And the number of characters is the length, and it's not infinite. But to fully answer your question, it's a much more subtle. It's a very good question. Other questions? Yeah. Well, so the first and the second and the third strings of this language in lexicographic order are these three in this example. That's all I'm saying. So obviously B is not there, and neither is BA, and neither is AAA. Because if there were, they'll appear before these. That's all. It's just an example. So the string B by itself is not in this language. Why? Because if it was, it appeared second. But the second thing that appears here is not a B. It's something that is later than a B in the lexicographic order, which means B isn't in this example language. That's all. Does that make sense? So the string B is not in this particular language that I'm illustrating in this example. In other languages, it may be there, but not in this one. Does that make sense? Okay. Any other questions? So again, what's the intuition about lexicographic order being so important about decidability is the fact that if you have an enumerator in lexicographic order that's spitting out strings, eventually you'll know that a string is not in this list because larger strings than it will appear, right? It's just like an airline saying, okay, the following passengers are ready to board, and we're going to list them in alphabetical order, and the others will, have to go on standby. And here's the alphabetical list, and they start naming names, Abrams and Barbie and Jones, and they're giving you an alphabetical order. But if your name is, I don't know, Klein, and they're already into the Joneses, you know for sure right there and then that you're not on their list. How many get that? Okay, good. That's what's happening here. Assuming it's in lexicographic dictionary order. If they gave the list in arbitrary order, and they rattled off names including Joneses, and you're a Klein, you still don't know. And you'll never know until it's done. Until the list is completely given and specified and uttered. You'll never know until the very last name. And if the set of names is infinite, you'll never know, period. Ever. Because there's always a chance that you will one day be mentioned, and you don't know when to finally say, I have no hope of being mentioned because some other names were. That's sort of what's happening here. Any other questions about this? Because we're about to prove another pair of theorems that's even more subtle than that, and then we'll prove Rice's theorem, which is generalization that you wouldn't even believe right now how deep and subtle that is. So we need to wrap our minds very tightly around these simple concepts first before we go into more abstract, deeper, more convoluted things, which we are about to. Yeah. Yeah. So if you just know that it's finite, but you don't know how many there are, you're still not sure when it's going to stop. Because, if there's 13 names that have been uttered, maybe there's 15 total. Maybe there's a Googleplex. Who knows? It could be very large, even if it's finite. So, all right. Any other questions so far? Okay. Next pair of theorems. If a language is recognizable, it can be enumerated, not necessarily in lexicographic order. So if I said lexicographic, I meant it. If I just said enumerated, I'm not saying lexicographic because it may not be lexicographic. So I'm very intentional about what I say. I choose my words very carefully. You should try to do the same. So if a language is recognizable, it can be enumerated in some order. I don't care which, lexicographic or not. At this point, the order doesn't matter. So if you have a recognizer, what is a recognizer? A recognizer says yes when it sees a yes. When a no comes around, what does a recognizer do, potentially? What is a recognizer allowed to do on a no when a non-string comes around? Yeah. It can either run on forever, or does it have to run forever? It may run forever. It's an option, but not a requirement. It's an elective. Right? So besides running forever, what else can it do? Not a trick question. It can just reject and stop. It can actually spit out the answer. No, and stop. That's okay. Or it can run forever and thereby not accept and thereby implicitly reject. Right? That's what a recognizer does, just to repeat what we said all along. Okay, so if a language is recognizable, there is such a process, a subroutine, a piece of code, an algorithm that does that. Either runs forever or says no on all the no's, all the strings that are not in the language. And whenever a string that's in the language comes around, it says yes, and it must stop in finite time and acknowledge and agree that the string is in the language. So definite yes in finite time on all the yeses, but if it's a no, it can either say no and stop, or it can run forever and thereby implicitly tell you that it's not there by running forever. Okay, that's what a recognizer. If you have a recognizer, such a subroutine, how can you build an enumerator from it by using it as a subroutine? Again, not very hard, but you got to say something. Silence is not the answer to this. How many understand the question? I don't want to be presumptuous. All right, that's just a few people. How many don't understand the question? How many understand the question? Right. How many don't understand the question? So a lot of you are just not voting. How many are listening to me? I'm just curious. Okay, good. I had to be worried there for a second. So I'll repeat it. That's fine. I'll repeat it as many times as I have to until you get a majority that says, yeah, I understand what you're even asking. And then I'll ask you to answer it. Right? I mean, I'm not going to ask you to answer something you don't even understand what I'm saying or asking you. Right? So here's what I'm asking you to do. We have a recognizer. It's a subroutine. It's a black box. It's an algorithm. It's a piece of code that recognizes yes strings, yes being strings in the language. And when a yes string comes around, it stops and says, yes, that's one of the strings that's in my language. If a string that's not in the language comes around, it says, no, it's not in the language, or I'm going to run forever if you're waiting, but I'll never say yes. And that's equivalent to a no. It's like a cold shoulder equivalent to, I'm not interested. Right? It's a passive-aggressive way to say no. Run forever and don't come back with an answer. It's better to say no decisively, don't get me wrong. But that's another way of doing it. Most of you may have experienced that in your lives. Somebody. Maybe your parents, maybe somebody else. So not saying yes is a way of saying no. Okay. That's what a recognizer does. How many get that? Okay, that's a bunch of you. Good. Now we're getting somewhere. All right. What's an enumerator? The other red word in this question or statement. An enumerator is something that spits out more and more instances of this set that you're enumerating. An enumerator for prime numbers will spit out a 2, then a 3, then a 5, then a 7, then an 11, 13, 17, and 23, and so on and so on. How many get that? That's an enumerator for primes. That's what a prime enumerator would do. Every language could have an enumerator. Some of them don't necessarily, but all the languages we've seen so far have enumerators. Like a set of primes, like a set of halting programs, right? Like a set of perfect squares, right? Like the set of all strings, sigma star. All these have enumerators. Now, when I say enumerator, I don't necessarily mean by lexicographic order. I could have printed out the primes not in order. So one way to print out the primes would be to say 2, 5, 7, 11, 13, 17, and 23, and so on. But I could have enumerated the primes a different way. I could have enumerated the primes 23, 2, 17, 5, 53, and 7. That's not in order, but I'm still enumerating all the primes. How many get that? Okay. Now, it just so happens that with the primes, I can enumerate them either in order or not in order. I have a choice. And it's pretty easy to jump around or do it in order, algorithmically. You have to write a piece of code for it. Some languages, not so much. Some languages, you can enumerate it, but never in order, ever. That's what we're about to prove here. Some languages, enumerating is easy. Enumerating in order is hard or even impossible. Give me an example of such a language. You've already seen one. A language for which enumerating in arbitrary order is doable. Enumerating in lexicographic order is impossible. How many understand my question now, this question? All right. So give me an example of a language that you can enumerate in some arbitrary order, but never, ever in lexicographic order. What do you guys say? Probably just guess which language we're talking about. Only one language is really weird so far. Soon you'll have many more examples of weird languages like that. So, any thoughts? Empty language? I can enumerate it in order by saying the first string is, I'm done. There is no first string, so that's order. But it's a very good try. What else? The halting problem. How many see the halting problem? All right. Why? Somebody else explain why. How can I enumerate all halting programs? Not in order, in some way of enumerating them. let me back up. How many understand what it means to enumerate a language? Okay, good. That's at least half of you. It means there's an algorithm that spits out strings from that language. That's like prime numbers. All right. The halting problem. How can I enumerate halting programs? All halting programs. Not in order necessarily, because there is no way to do it in order. But there's a way to do it not in order. This is not a trick question. This is not extremely deep given everything that we talked about so far. Could you write a piece of code right now that by, say, this afternoon or tomorrow, when you run it, it'll print out all valid halting Java programs? How many can imagine how to write such a piece of code? Okay. Perfect record. That's maybe one person. Oh, question. Okay. What is it? I'm not saying anything about size. I'm just saying have a piece of code, just like the code that prints prime numbers, but this new piece of code will print halting Java programs. How many understand what's a halting Java program as opposed to a non-halting Java program? I mean, it's one that doesn't have an infinite loop in it, that if you ran it, it would stop. That's what that's what a halting program is. I don't care what it does. I just care that it stops as opposed to run forever with an infinite loop. I'm not asking for much here of a program. I don't care exactly what it does or if it does it correctly. I just care if it halts or doesn't halt. That's probably the simplest thing you can expect from a piece of code, is to halt. Never mind do something or do something correctly. Okay. So how would you write a piece of code, an algorithm, that will print out all halting programs? How many see how to do that at this point, since you have a few minutes to think about it? Okay. 3, 4, 5 people. All right. The rest of you are about to be enlightened in the next 3 minutes then. That's good. That's why we're here for. I was hoping it'd be more than 3 people. How many understand my question? Okay, that's good. That's progress already. You understand what I'm asking? Good. Sometimes I'm not even sure about that, so that's reassuring. Okay. Any thoughts? How would you write a piece of code that prints out all halting programs? You can do it in Java, C, C++, Python, whatever you'd like. The language doesn't matter here. It's not about the language. Yeah. Yes. Otherwise, you'd be printing out sigma star. That's a very good question. He's saying, does it have to be halting programs only? Can I print also non-halting? In other words, am I supposed to tell the truth and only the truth? Or just the truth and also a bunch of lies besides? Yeah. That's why in court they distinguish these cases. If you were just allowed to print the halting programs and also lots and lots of other stuff, the problem is much simpler. Just print out sigma star. Sigma star is all strings, including halting programs, but also including non-halting programs, and in fact, including non-programs. Like Shakespeare's Hamlet will be printed out too, because that's in sigma star. How many get that? Shakespeare's Hamlet is in sigma star. And that piece of code will print that out too. But that's no big feat to do that. The trick is not just to be right. The trick is also, as a separate matter, not to be wrong on other things. Right? If you just had to be right, and that's it, and that was enough, that would be very easy to do. If you take an exam saying, say multiple choice exam, answers is A, B, C, or D, you can just say all A's. Just answer every question with the choice A out of the 4 choices, A, B, C. You'll be right a bunch of times, but you'll also be wrong a bunch of times. And that's no big feat to do that. Okay, so yeah, you got to print all halting programs, and you better not print any non-halting programs or any non-programs at all. Those don't get printed. Yeah, what do you say? I'm not saying any order you'd like. So if you want to do it by that order, fine, or some other order, that's fine too. But your piece of code better print out all halting programs and nothing but halting programs. And I don't care how long it takes them to halt. They need to be printed out on this master list. It's close, yeah. What do you say? Which program are you compiling? Okay, that's it's getting very close. Which programs are you compiling? Let's be very specific. You're an enumerator, you have no input. You fire up and you're on your own. Which program are you running? Where is that program? And where is this set coming from? The set of all programs in the language. Algorithm to generate them. What's your piece of code that generates the next program in the language? How do you do it? How many see what he's trying to do? He's trying to generate all programs in the language, and for each one of those, see if it holds or doesn't hold. It's very good. I mean, all of you are on the right track. You know, all of you are on the right track, but let's kind of nail this thing down real tight. Yeah. Yeah, exactly. So generate all of sigma star, all of it, one string at a time, in lexicographic order. That's easy to do. How many see that? Yeah, a few lines of code will do this. Generate all possible strings, from small to large. For each one of those strings, assume it's a program. Some of it may not be a program. Some of it may be Shakespeare's Hamlet or the textbook of this course or whatever. Those will all get printed. How do you know which one is a program, which one isn't a program? Of all sigma star strings coming out. Yeah, run them through the darn compiler. You got a compiler subroutine that you can call. You all have it on your systems, right? Every string comes out, run the compiler on it. The compiler always comes back and says, yes, it's a valid program, or no, there's a bunch of syntax errors. For those, forget those strings that have errors in them. Shakespeare's Hamlet will not compile under C++ compiler. How many get that? You'll get a bunch of errors. Don't get me wrong, it's a pretty good string, and there's lots of plays based on that string, and it's kind of interesting and historical and all that, but it's a lousy C program or Java program. Of course, it was never intended to be that. So, sigma star, one string at a time come out, each one run through the compiler. The compiler will tell you if it's a valid program or not very quickly. For each one that it says it's a valid program, what do you do next? One word. First, run. Yeah. First, run it, because you're looking for halting programs, right? So run it, or execute it, or simulate that program, however you want to think about it. For the ones that you run that halt, then what do? One word? Print, yes. So run and then print if it stops. Now, if you run it and it doesn't stop, what do? Only supposed to print out halting ones. So there's an issue here. But we're almost there. Let's backtrack a little bit. For the ones that sigma star strings that don't make it through the compiler, and the compiler chokes on and says lots of syntax errors, what do you do with those strings? That's the easy case. Don't print them. There ain't one of those programs that are going to hold. They're either nonsense, they don't compile, they're not a program, so you don't need to print them. So move on, get to the next string. How many see it so far? We're almost there. How many see there's still an issue here? The issue is subtle. What's an issue here? What do you say? Yeah. So if you happen to stumble upon a syntactically correct program that has an infinite loop in it, it will not halt. And when you run it, you will not halt either. Your run will go forever. When will you know that you're going to be running forever with this thing? You can't know because the halting problem is undecidable. It's unsolvable. We've already been through that. So there's no way to tell if a program runs forever or not. But you're running it. You're simulating it now. So if it runs forever, in general, you will run forever too. You'll never get to the next string that halts because you're stuck on this string that doesn't halt, that runs forever as a program, and you were going forever to infinity along with it, and you'll never come back to the next string that may halt as a program, and so too bad for you. That's not an algorithm. How many see that problem? Good, that's a lot of hands. I like that. How do you fix this thing? There's a way around, there's an end run around this problem. How many can, or who can tell me about how to avoid this situation of running forever? I want some more people to participate. I get the same 4 or 5 people. I appreciate that. I'm pretty impressed, but I want other people to have a chance to feel the rush of speaking up. And whether you're wrong or not, that doesn't matter. You already get points for courage for speaking up because everybody's afraid to say anything. And you don't win anything like that. Yeah. Program, and you can't just arbitrarily modify the program, right? You need to know if the program holds or doesn't hold, and if you modify it, it's no longer the same program. Okay. Separately or mark them, but how do you know which one holds and which one doesn't hold? And you need to know which one holds or doesn't hold to be able to print all the halting. So what do you do when a program runs forever and you're on it simulating it? How do you avoid running forever with it and thereby precluding yourself from identifying any other programs that may actually very well halt that you need to print out? You don't want to get dragged into infinity with a bad apple. You see what I'm saying? Yeah. Yeah. Start a new thread. And don't simulate that one program forever. Yes, let it run, but start a new thread with the next candidate that may halt. And that one may run forever too. So what do you need to do next? Yeah. Make another thread and another thread. Run them all in parallel. Right? All the strings that pass the compiler test, run them all in parallel as separate threads. And the ones that halt, you will know because that thread will terminate and says, "Yeah, I'm done." And so you say, "Fine, I'm going to print you out." The ones that are still running, keep running them. And the ones that run forever, that's okay because you're running other things alongside the ones that are running forever, and it doesn't matter that those are running forever because none of them will ever starve for your attention as the simulator. You will simulate all of them for long enough that if any one of them ever would stop, you will know because it will eventually get enough cycles because you're round-robining between all of them in a cyclical fashion, and you keep adding more and more and more at every step. How many understand this strategy? It's a parallel execution strategy. It's an algorithm, but parallelism here is essential. You can't just take one and simulate it forever and wait to see what happens because eventually will never come. And the other ones you'll never get to. That's the problem with rushing towards infinity headlong. You may never come back from that. It's a pretty deep rabbit hole, infinity. Yeah, question? Yeah, that's an alternate way of doing it. So when you say parallel, there's lots of ways to implement this parallelism. So what he's saying will also work. So what he's saying is, okay, run the first one for 1 second. If it holds, fine, print it out. If it doesn't hold, abort it. Run the second one for 1 second. If it holds, print it out. If not, abort that. Then go back to the first one, run that for 2 seconds. If it holds, print it out. If not, abort that run. Then print the second one for 2 seconds. Then print the third one for 2 seconds. Then go back, print the first one for 3 seconds, or run it for 3 seconds. 3 seconds, 3 seconds. The fourth one for 3 seconds also. Then run the first one for 4 seconds, the second one for 4 seconds, 4 seconds, 4 seconds, and the fifth one for 4 seconds also. Then go back. Run the first one for 10 seconds. the second one for 10 seconds, 10 seconds, the third one for 10 seconds, and so on and so on. And run more and more of them for longer and longer and longer. So right now, you're not even doing things in parallel per se. You're just running one at a time, but you deliberately are aborting them if they run for too long, and then running other ones, give other ones a chance. And if they don't terminate on their own, abort them on purpose, and then keep going and giving more and more candidates a chance and jump around between them. And eventually, every candidate program will have enough runtime that if it ever chose to stop on its own, it will. How many get that? Okay, good. That's a lot of hands. I like that. Yeah. So remember, these are Turing machines. These are, there's no user in a Turing machine per se. So these are programs that just run. They don't stop and wait on anything. So there's no users, and they're not waiting on a website to come back to them. They're not sending packets. They're not sending an email and wait for a reply. They don't try to text somebody and wait on some, So they don't do the stuff that your iPhone does or your smartphone does. These are just programs that run on their own and either terminate or don't terminate, and they don't wait on anything, including a user. But it's a good question, and if it waited on user input, then the simulator can give it an input, can generate an input for it, generate a random string and says, here's your input. So there's a way to handle that too, if that's what these programs are allowed to do, is to wait on stuff. Any other questions? Yeah. No, because if it ever halted, you remove it from your list. You'll never simulate it again. So you only print it once. You just keep a record of that, just larger and larger array of copies of programs that you already printed. And when something got printed, you never generate or run that again. That's all. Good question. So, any other thoughts or questions? So we had two solutions here. One is start parallel threads and more parallel threads. The second solution is don't even think about it as parallel. Just jump around between the two, all the programs. Just bounce around, round robin, getting more and more candidates to run for longer and longer and longer. One at a time, no parallelism here. No threads here, just one thread. But the two are equivalent. Abstractly, algorithmically, the two solutions are kind of the same. Because what is a thread? A thread is just another subroutine that you're running together with the first subroutine, and there may be other threads too, but it's not really necessarily parallel per se. It's not simultaneous necessarily, right? If you have only one processor, it can still run 50 threads, and it looks as if it's doing all of them at the same time, but really it's just jumping around, just like in the second solution. It's jumping around, simulating the different threads for longer and longer and longer, and they all kind of co-evolve together in their own execution threads. And you can either think about it as parallel or serial, time-sharing, bouncing around, dovetailing, however you want to think about it. The two are sort of equivalent algorithmically. How many see that? That's what your computers do. They pretend to be parallel, but they're really serial. They're just serial so fast that it looks parallel and feels parallel. That's okay. That's fine. All right. That was like pulling teeth a little bit, but we proved this theorem. We said that if you can recognize a language, you can enumerate it. How? Well, run all these recognizers together on all the strings, round robin, multiple threads, time slicing, however you want to think about it. And eventually, when one of the recognizers has a hit and says, okay, fine, it's a yes, you print it out. And you never run that recognizer again on that string that you just recognized because you already got it. You just keep running it on more and more strings, different strings. How many see the theorem now? Okay. I think I lost like half the hands I had a second ago. So we couched it in terms of halting programs, all this long explanation. But it generalizes to any recognizer, not just recognizer of halting programs. If you got a recognizer that tells you when it sees something in its set that it's supposed to recognize, That's like simulating the halting program by running it. Right? That's a recognizer for halting programs. But the recognizer doesn't have to necessarily recognize halting programs. It can recognize whatever strings it needs to recognize. If you run it on a string, it'll recognize it if it's a yes. So run all the recognizers in parallel or in different threads, or round robin, jump, time slice, time share among them. Run each one for longer and longer and longer, and give other strings a chance all the time. New ones, give them a chance. And eventually, some of the recognizers will say yes, and those are the ones you print. The ones that run forever, just let them keep running. The ones that say no, what do? Don't print. And you don't have to run those again either. And eventually, everything that's a recognizer says yes on will be printed. And nothing will be printed except things that a recognizer says yes on. It's an if and only if. Only the things that get recognized will ever end up on your list, the output list. How many see that? Okay, good. Any questions? If the recognizer says no, you know that string shouldn't be on your list. You never simulate that string again, and you move on to other things. So whatever the recognizer says, if it says no, that string is out. If it says yes, it's in. If it runs forever, it's undecided, inconclusive, let's call it, and you just keep running. Not right now, but later you run for longer and longer, just in case it will eventually stop and say yes, but you don't know yet. This is how you prevent the bad apples from contaminating the good ones. The ones that run forever will not get in your way this way, because you're giving others a chance along with the ones that potentially will run forever. You don't put all your eggs in that one basket of that one thing you're trying to find out to the exclusion of trying other options. This is like the venture capitalist model of computation here. How many get that analogy? Good. What do venture capitalists do? They don't know which company will flop. So they don't take all their money and put it in one startup and say, okay, go, we'll see what happens. That's a bad business strategy. They start up 10, 20, 30 companies. They know that some of them will either flail forever, never generate a profit, or some of them will just sink right away, but they don't know which. And that one company that's a Google or Apple or Twitter or whatever, one or two of those will pay for all the other 29 or 28 ones that fail or run forever or fail to make a profit. So the good ones don't have to wait on the bad ones. And in real life, you use that strategy all the time, not just for venture capital and business, but even in social life. Right? That's why it's good to have a bunch of friends, not just one friend. Right? What if they go? What if they die? What if they diss you? Then you'll be all alone. And, it's a hedging strategy. It's hedging your bet. And I'm not saying it in a derogatory way. I'm just saying it's just a good strategy. So here you're hedging your bet against bad ones that will run forever. Algorithmically, that's exactly what we're doing here. All right. Any other questions about this? This is a very general technique. And we just gave examples from real life where you do this all the time. You do exactly this technique. Not just in business, but in your social life. Yeah. What's that? Yes, the enumerator may very well run forever, especially if this language is infinite. That's okay. We're tasked with printing out all the strings in the language. So if the language is infinite, we have to run. We not just may run forever. We have to run forever. Otherwise, we'll never be able to print them all. Right? So this enumerator will never stop. It still has work to do at any stage, no matter how many strings it prints. After Googleplex strings, it'll still have strings to print out because the language is infinite, and it better keep going. So the enumerator can never stop if the language is infinite. Even if the language is finite, the enumerator will never stop. Why? Because it doesn't know that it's finite. And it may print only 3 strings, and there may only be 3 strings in the language. But he has to try the 4th and the 5th and all of sigma star. And that's okay. But it accomplished its task. Remember what his task was, the enumerator's task was to print out all the strings in the language and to not print out any strings not in the language. Right? So you have to tell the truth, but you also, and separately, and even more importantly, tell nothing but the truth. And these are two separate things. So, yes, the enumerator will run forever. It's a good observation. How many see that? And that's not a problem. That's what it does. We never said the enumerator has to stop. In fact, often it won't stop. And actually, the way we stated this article, it will never stop. That's okay. It's okay for a program not to stop. Not stopping or running forever, it's not necessarily wrong. It's not necessarily bad. Give me an example where it's good to run forever. In fact, it's required to run forever, and if you ever stop, it's bad then. Operating systems, and there's many other examples. Your pacemaker code in your chest. Hopefully none of you have to do that, but that runs 30,000 lines of code. It has an operating system on it, and that thing better not crash or stop. Otherwise, you'd be in trouble. Some codes better run forever. Better never stop. That's part of their specification. That's okay. So it's not that running forever is necessarily bad. Okay. All right. Second part of this theorem. The other direction. So if a language could be enumerated by some Turing machine, then it's recognizable. How many can see how that would work? So it's the other direction we're proving. So what we just finished doing is saying if it's recognizable, you can enumerate it. And by the way, before we even say the second theorem, which order do the strings come out of this enumerator that we constructed? The length of the program, the length of the string. Anybody else want to chime in on that? What order are these strings coming out in? It's the length of execution time. That's basically true. Let me ask more specifically. Are they coming out in lexicographic order? Are they coming out by length order of the string or by dictionary order of lexicographic ordering of the string? How many say yes? How many say no? Good. That's a no. It is related to the execution time of the algorithm, but that's nothing to do with the length of the string itself, that it's being recognized or not recognized. So it's not coming out in any kind of lexicographic order. All right. So next theorem, if you have an enumerator, if you have something like this that spits out strings in arbitrary order, not lexicographic order, but any order you'd like. If you have a subroutine that spits out strings that are in the language, and it never spits out strings that are not in the language, I'll often say that just to reinforce the fact that when you need to do something as a task, implicitly or even explicitly, not only should you do that task, you shouldn't do anything else except what is being specified if you're a programmer. Okay? So if you have an enumerator that spits out strings in any arbitrary order, from it you can build a recognizer by using the enumerator as a subroutine. How do you do it? What's your technique or algorithm then? How do you build a recognizer from an enumerator? At this point, it shouldn't be that hard. We just saw 3 other examples, the last 3 theorems. Right? These 2 theorems and this theorem. Now, what about this 4th one? How do you build a recognizer from an enumerator? Let's be a little more specific. So a string comes in the door, and you're the recognizer. You need to recognize yes or no of that string that comes in the door. That's your input string. A recognizer has a single input string to it. And it's supposed to say yes, no, or run forever. That's what a recognizer does. So a string comes in the door. Sounds like the beginning of a bad joke. A string walks into a bar, and you're supposed to recognize it. And you have an enumerator in the subroutine that you can exploit. No, I didn't say a string is enumeratable, a string is recognizable. I said about languages. A string is neither recognizable nor enumeratable. Neither is my right shoe recognizable nor enumeratable. My left shoe is neither prime nor composite. So the property of enumeratable, recognizable, regular, context-free is a property of languages, not of strings. So that's a very good example of a type error. Don't do that. But I appreciate your speaking up. So you're more courageous than those who are just sitting there quietly, afraid to say anything. Yeah. What's that? So if a language is enumeratable, yes, there's some enumerator that spits out strings of that language, not necessarily in order, but all the strings will eventually be spat out by that enumerator. Okay, so it's a good try. What else? Anybody else? So a string comes in the door, and you're the recognizer. You don't know what to say about this string. You need to say yes, no, or run forever, but that's your job. You're the recognizer. You don't know how to do it, but you have an enumerator for the entire language from which that string comes from. What do you do? How do you exploit the enumerator to do your recognition task? It's a subroutine. Right? The enumerator is a subroutine. You can fire it up. It'll start enumerating things. That's what it does. That's what an enumerator does. It spits out strings on a long list. Yep. Yeah. So take that input that comes to the door. Fire up the enumerator. Strings will start to be spat out by that enumerator. That's what enumerators do. They spit out strings one after the other, not necessarily in order, but they spit out eventually every string that's in. Eventually it will be spat out. All right. So start firing up the enumerator. Strings will come out. Compare each one to the one that came in the door. If it's equal to one of them, what do you do then? Easy question. Accept. So yeah, I got it. It's part of the language. If it's not one of those that's being enumerated right this second, what do you do? Easy question again. If it's not equal to the first one, it's not equal to the second one, and the numerator keeps going, you just keep enumerating. Keep running the numerator. If that string is equal to any one of them, you say, yes, I accept. If it's not equal to the first, the second, the third, keep going. If it's in the language, the enumerator will eventually spit it out. How many see that? That's what enumerators do. And eventually you'll see that it's spat out. You'll compare it to the one that came in the door. And you'll say yes, and you'll be correct in recognizing it as a yes. If the enumerator never spits it out, what will you do? Or more precisely and subtly, what won't you do? You will not halt, true. And if you don't halt, you also won't accept that string because it's not even equal to any one of those coming out of the enumerator. And you will run forever too, you being the recognizer. You will run forever along with the enumerator that will never give you the string that you're looking for. And so you'll run forever, but running forever is not accepting by definition. And so you will not accept either. And again, you're performing your job correctly because you're not accepting that string because it doesn't show up on this long, long list of strings that keep coming out and more of them coming out. And thinking fast, they came at last, and more strings will come out. But none of them will be the one that came in the door. So you will never flag any of them as the candidate. Then you'll keep running the enumerator, and that's okay. Now you're running forever. But now you're a recognizer. You're allowed to run forever, and that's a valid behavior for a no. How many get that? So we just build a recognizer from an enumerator. Okay, so what have we done? Two theorems. One is we said if you have a recognizer, you can build an enumerator from it. If you have an enumerator, you can build a recognizer from it. So the two concepts coincide. They're one and the same thing. They're the same characterization. They're two different characterizations for the same phenomena, for a language being recognizable. So a language is decidable if and only if it has a numerator in lexicographic order, and a language is recognizable if and only if it just has an enumerator in any order you'd like, in some arbitrary order, I should say. So we have 4 theorems, 2 pairs each, 2 groups of two groups of pairs, and together they're complete characterizations in 2 different manners of this decidable versus recognizable languages. Any questions about any of that? I know it's perhaps a little abstract. Maybe you haven't seen that before, but we just proved 4 theorems. We have 2 pairs of characterizations that are equivalent in pairs. Again, the first pair, decidable, lexicographic order, those 2 characterizations give you the same set of languages, the decidable languages. Second pair, recognizable and enumerated in any order, in some arbitrary order, not necessarily lexicographic order. The 2 are equivalent again. Okay. How many sort of get at least most of what we just talked about the last half an hour or 45 minutes? Okay, that's a bunch. I wish it was 2/3 of the class, but anyway, so read about this in the book, study it more, think about it, wrap your mind around it. Very important. So this comes from the book from page 165, chapter 4. Here's the numerators. Tells you the whole story in different words. But please read the book. It can't just be me explaining it to you. It's not enough. Work problems, there's problems in the problem sets. And we're going to generalize all this. This is still shallow water, so get real comfortable with this. All right, see you next time.